Hello dear friends and welcome to another electronics tutorial. Today we'll be discussing inductors and their role in electrical circuits. So first of all, why do we use inductors? Inductors are mainly used in power supplies and in filtering for signal transmission. Their main feature is that they pose sudden changes in current. So any change in current through the inductor is opposed by the inductor through a voltage drop. So this means that it will try to keep the current going through it as constant as possible. The main way that an inductor does this is it stores the energy going through the inductor in a magnetic flux. So it creates a flux around the ferrite material and around the coils, and then this flux opposes any change in this current going through the inductor. Now, the main or one of the main usage for this is for filtering ripple current. Ripple current can be caused by DC motors, it can be caused by a microcontroller, by any component, any switching component that will suddenly draw a lot of current. The inductor would limit this current and would prevent a sudden change in the current going through it. There are multiple types of inductors. So here I've placed a couple: air core, which has no ferrite material, iron core, ferrite, which is, from my point of view, the best type of material. I work with a lot of power supplies, so ferrite core is one of the best types of inductors that I use, and a variable inductor, which you can set the values for the inductance by turning a knob or some way mechanically. So here are a couple of pictures just that you form a good image about inductors. This is an air core inductor here. You can see that the coils are don't have any core, any ferrite core or any ferromagnetic core here. So the current goes through here. All these wires are isolated from one another. So one of the causes, so if, for example, some of these wires, the isolation would break in mounting or something, it will cause a short circuit and would damage the inductor, and the inductance will go down quite fast. Iron core inductor, so the iron core is in the middle. Ferrite core, which is one of the most common types of inductor and also my favorite, and bobbin-based inductors. So bobbin-based inductors, this is a SMD surface mount device inductor. You place this on a PCB. Here is the input. The wire is then coiled and then goes through the spin to the output. Variable inductors, very used in radio transmitters. Here they have this line that would go through the inductors, through the windings of the inductor, and then it would create a smaller inductance. So as it is here, um, it will have an inductance going only till here. If this is if this stator is moved to the left side, we'll have a smaller inductor till here, and here would be the highest inductance this component can have. And multi-layer ceramic inductors. These are very common used in filters for high-speed signals. Um, Here they are used for communication lines, for different protocols of communication, and these are widely used in, let's say, in computers where you have a lot of high-speed lines. You have these types of inductors that have a very small inductance, but they are easily mounted on the PCB. Regarding parameters, I have taken here an example for an inductor. This is a 10 microhenry inductor with a plus minus 20% inductance tolerance. So 10 plus minus 20% is quite high tolerance for an inductor. This means that this component can be from 8 microhenry till 12 microhenry, so it's quite a large uh, limit for the inductance. But most inductors have this high tolerance, so you will see that there are most of them have in tolerance above 20%. Regarding the rated current, this particular inductor is rated at 2 amps current, so the maximum current going through the winding should not exceed 2 amps. This is a quite high current, and from my experience, I would not go for any inductor. I would not go with the maximum current because we are very close to the saturation current, where the the behaviors of the coil becomes a simple wire and it just heats up. It doesn't provide any additional inductance. I would go, for example, with the 1.5 amp current through it, just that we have a buffer of 0.5 amps where, for example, for shutdown behavior or startup behavior. Regarding the DC resistance, so because it's a wire, the DC resistance is quite small. In this case, the maximum one is 49 milliohms. So for this component in particular, you can take 49 milliohms and yeah, let's calculate the voltage drop for a 2 amp current. This would be about 48 milliohms times 2 amps would be about 0.1 millivolts time. So and the power for this component would be 0.1 millivolts times 2 amps would be 0.2 watt power dissipation. So this is quite okay for an inductor. Also quite important is the self-resonant resonant frequency. So the self-resonant frequency is the frequency where the inductance of the inductor and the parasitic capacitor have resonance, go into resonance. So you have to be very careful about this 26 megahertz. So not to have um, not to go to this frequency because here it would have very high impedance, and of course impedance means that it will act as as an interruption in the circuit, and this would not help anybody here. And the maximum operating voltage is 120 volts. So this means that the operating voltage usually is done by the isolation between the wires. So if you go with more than 120 volts, usually this isolation will break, causing the component um, to burn and be destroyed here. Going forward, I added a graph regarding the typical inductance versus current characteristics. So this is very important that we go through it. So here you can see that the inductance as you go over the 2 amp drops quite significantly here. And as I said, I would not go anywhere above 1.5 amps for this component, just that we include the startup behavior, shutdown behavior, because the for the coil you will have or you will require these types of behavior. And of course the impedance characteristic. So you can see here, this is a calculated impedance for the coil. So at 0.1 megahertz, so 100 kilohertz, this is about, let's say, 1, 2, 3, 4, 5, 5.5 ohms, right? And then it starts going up as you go here at 10.5 at about 15 megahertz. it starts going up. So here is the resonating frequency for the coil. So stay away from the zone. The difference between 15 megahertz and 26 megahertz, it's about 10 times more impedance. So here would be the coil would act as an interrupt in the circuit. Okay. Regarding some formulas for the impedance, so the inductor's impedance is 2 times pi times the frequency where you are measuring times the inductance. So in this case, I've taken a 100 kilohertz frequency and a 10 microhenry coil, and the whole um, 100 kilohertz times 10 microhenry, it's about 2 times pi, which is about 6.283 ohms as an impedance. And you can see it here, the supplier for this coil even has a lower impedance than the calculated one. So this means that this is quite a good designed coil. One other thing that I would like to mention before we go into the simulation area is that this coil is shielded. So having a shielded coil is tremendously important because having a shielded coil, this coil would not influence any other components that may be mounted quite close to it. So it would have less emissions from EMC. Um, and you can see the difference between this one and this coil here, which is this is a simple unshielded bobbin-based inductor, but it doesn't have the lateral shields, which are very important for EMC behavior. And this one has everything is cased in a ferrite material, so this reduces significantly the emissions. Okay, so this is about inductors. In the next part of the video, I'm going to go together, we're going to go over some circuits with inductors. So for this, I'm going to use Orcad Capture Chess. It's quite free for less components. If you have more than 50 components, I think you have to pay for it. And also has a free student license if you are a student. So let's go into the simulation. Okay, so now we're going into the simulation part. This is the ORCAD loading screen. Let's start by creating a project. To create a project, you have to click here or Control New. Let's name this Inductor Project, and select the location you want to place the project, and be sure to click the enable PSpice simulation because the PSpice software is the one that's going to do the simulation. Okay, so after we click OK, we are asked if we want to use some standard signals or do we want a blank project. I usually go with a blank project. You can also get some standard symbols already added to the schematic, but I will guide you through creating a blank project. Then we click OK, and the ORCAD loads the project. On the right side, um, yeah, it's the menu with all the parts. If you click on the first button here, the place part button or the P button, here you'll find all the parts that already have a model for this. If you do not see any parts here, you have to click here to add a library and make sure that you select the correct library path here. So it's usually tools, capture, library, and pspice. After you've seen these libraries, you will see that all of them are OLB files. You can just Control A and open, and ORCAD will open all the libraries here. So let's start by adding a power supply. So for the inductor, we can use um, an estimated sine V sine power supply that will create a sinus wave output. So mainly this power supply will create an sine wave on an offset voltage. Let's say we want to test our inductor to see how it filters the signal. We can put an offset voltage of, let's say, 12 volts. So on top of this 12 volts, um, we will have a sine signal, and let's put a 500 millivolts sine wave on top of this. For the frequency, um, we can go with 100 kilohertz, and also for the AC, it's the same because we've discussed about the impedance of an inductor at this specific 100 kilohertz frequency. Okay, so this means that we have set our generator to generate a voltage level of 12 volts. On top of this, we have a 500 millivolt um, sine wave, which is at 100 kilohertz. Great. Now, all we have to do to make this power supply be real is we have to add a series resistor because all power supplies have an internal resistor. I usually place this internal resistor for the power supplies at about zero point 0.1 ohms, just that we have the correct impedance for this component here. Okay, now let's add a coil. So coil, we just have to press L and we get an L analog coil. The L analog is a standard coil which we can change the inductance. So we can, for example, let's put here 100 microhenry just to have a bit more inductance. Okay, and for the purposes of seeing how this works in a circuit, we will need a load. So let's place a resistive load. The resistor is or appears when you press R. Here it's R analog for from the component library. So let's see here how much current do we want to draw through this resistor. So let's say we have a 12 volt supply and we want to drive 2 amps from this. So we have 12 volts divided by 2 amps. This means 6 ohms resistor. So let's place a 6 ohm resistor here. Okay, great. One last thing we have to add is the ground or reference. This would be picked out from the ground um, components on the schematic. So you have to just press the G key and it's 0 dash cap sim. You will know because it has the 0 here. That is the ground reference. Now let's connect everything. So for putting a wire, it's W on the keyboard. Just press W and you will get the cursor will change from a mouse pointer to a target cursor. Okay, and now we have connected everything. Great. Let's see how this circuit will run in a simulation. And for this, we have to create a simulation profile. On the top side, you'll see a new simulation profile button. Let's call our simulation Sim1. Click Enter, Create. And after we create the simulation, we need to edit the simulation profile. And here, let's place 10 millisecond transient domain analysis with the sampling rate. Yeah, we can put, so for 10 kilohertz would be about 10 microsecond period. So we can put 1 microsecond. We will not be looking at every every step that the simulation will take. Great. So everything is done. Let's run the simulation and see how the signals look. So PSpice has loaded. Let us place a cursor here and see how the signal is looking. So this should be, you can see everything is scaled on 12 volts, and this is a beautiful sine wave. Not so beautiful because of the sampling rate, but it's quite clear. Because we have a zero point 0.1 resistor, is going to be just a bit low between because of this resistor, but it's okay. It demonstrates and proves the purpose of the simulation. Okay, so this is the input signal. Let's see the output signal. So output voltage levels after the coil, and we can see a much smaller ripple here. So this is about, let's check. So this is about 8.7, 8.8. This means that this is 20, 40. So would be 20 plus 20 plus half of a decade. So this means that this is about 100 millivolts ripple compared to one one full volt ripple. So it's 10 times smaller as a ripple current, as a ripple voltage. Okay, let me zoom in so we can see it a bit clearer. And one other thing you can observe here, the current has been dephased because of the coil, and this means that the input current is dephased by this by the output current here. Okay, so this is great. This is a very good observation. Let's create a comparison between this model, let's say. Let's also Control C, Control V this model and remove the coil. See how this is actually working. And then let's create another model or another alternative, Control C, Control V, where we add a filtering capacitor on the output, just to see how the whole system would look filtered through a capacitor. So let us place a 470 microfarad capacitor here, just to see as a comparison to a single inductor, to have also a capacitor filtering this this input. Okay, so let's delete this trace and run the simulation. It has run. All Now we need to do a comparison. So this is the input. Let me add a plot to window. This is the inductor. So the following one is only the inductor. And then this one is the inductor and the capacitor. So it's it's night and day between these three. So this is without anything. Let me zoom in. So this is without anything. It's 1 volt peak to peak. This is 100 millivolts, and the other one is in the orders of millivolts. So it's 11.803, and this is 11.803. So we are discussing with the capacitor, we are discussing very small ripple here. Very small ripple in in microvolts area. Okay, so this kind of is the main role for inductor in the circuit, is to filter. Um, Let me fit this. So this the the role for it is to filter and to determine kind of clear the input or the high current demand between the load um, and the input current. So that being said, I would like to thank you for your time. Wish you learned something in this short tutorial. And if there's any other schematics that you would wish me to analyze, please feel free to comment or write me. I will try to create as many simulations and projects as possible. Thank you for your time. Wish you a great day.